So this is the second SIM-related talk today. It's focusing on over-the-air stuff. I mean, in the industry, everybody says OTA, but like, what actually does it mean in detail, and how does it work? So this tries to cover that to some extent. Once again, like in the previous talk, I'm not a global platform and not an over-the-air expert. I'm just playing with it occasionally every couple of years. It's again not a basic talk about SIM USIM stuff, so please check out some of the more basic talks if you need some more background. So for waking up, I have a single diagram with white background. All the other ones will have dark background. So what does over the air mean? Basically, you have some kind of application somewhere. I called it an off-card entity in the previous talk in global platform. So some kind of application, then there is some security processing, a transport mechanism, a receiving entity, and a receiving application. So here the eUICC is on the left hand and the bank is on the right hand side, but it can be the other way around. So the design of all of this is in a way that there is a part of it that's specified in a transport independent way, and then there are transport specific adaptations. So for example, over SMS, over USSD, over TCP, over HTTPS, there's all these adaptations how this can happen. Now maybe bit sort of why one would do that in the first place. Well, it's primarily to update contents on the card. Yeah, I think I have a slide later on about this. So the transport mechanisms, the most commonly known one is SMS. Well, specifically SMS point-to-point, that's SMS-PP, to differentiate it from SMS-CB, which most people just call cell broadcast, which is also specified, but I think it's not really used in production because it would require that all of the SIM cards have shared keys, right? Otherwise, how would you broadcast something to cards? So, yeah. USSD is another alternative. I'm not sure how much that is used. It's of course faster than SMS since it's session-based and you can send quickly like answers, request responses back and forth to a given SIM card. There's also the so-called bearer independent protocol, which is specified over circuit switch data, GPS, Bluetooth, and IRDA. I guess it's not really used anymore. Today, you really see, I think, SMS to some extent, and the HTTP, basically the most modern transport mechanism at the bottom. That's my understanding, at least, of the present situation. Yeah, there we have the use cases. So the primary ones, and those that are fully specified in the 3GPP specs, is remote file management and remote application management. Remote file management, well, the name implies, it's obvious. You remotely want to enable, disable, resize, overwrite, read whatever file in the card file system. So as an operator, for example, on the SIM card, there's a preferred roaming operator list or a forbidden operator list. And if you change your roaming agreements, then there might be a reason for updating those files to make sure that the phones don't try to register on networks that you don't have roaming permission to, or they prioritize certain networks when they're in roaming and so on. So something like this, or other configuration changes on the SIM card file system, basically. And when I say SIM, of course, this includes eSIM and USIM and all the flavors of it. Another use case that's also where this has been deployed is in the context of so-called multi-IMSI cards, which are used for a certain, mostly, I guess, low-cost MVNOs in roaming situations that don't have roaming agreements with everyone, where then basically when they detect, let's say I'm traveling to the UK with my SIM card and I'm registering, then they detect my in Germany issued IMSI now registers in a UK network, and they have a different roaming agreement with different IMSIs where they get a better price. Then they basically provision another IMSI on my SIM card remotely, and that basically includes rewriting the ef.imsi on the card. And then the card basically tells the modem to restart because the content has changed, and then the phone registers with a new IMSI to the network, which offers preferential roaming charges. So that and remote application management is the installation, update, deletion of applets on the card, and then actually you also have any kind of remote interaction with arbitrary applications on the card. I put Java here because in reality, but of course it could also be non-Java applets on the card. So it's also some kind of generic mechanism how stuff on the card can communicate with stuff off the card, whatever that might be. In the future, I think one common application that we will see is in the EID, the electronic identification context. So that I think will be very common in that. So, okay, how does this look like? We have the abstract generic part called the secured packet structure. This is for the command packet. It's actually quite strange that there's the generic spec and it already gives you the length of the various octets. It doesn't strictly say they have to be in this order. And also then the specific transports sometimes override the sizes of the how many octets a given field has. So take that with a grain of salt. So actually I think the number of octets is not so relevant here, but it's more like what does such a packet contain. So we have the identifier that this is a command packet, okay, like a message type. We have the length value of the packet. Okay, we have a header identifier, header length. That's sort of all generic stuff. I don't need to explain that. And then we have something called the SPI, which is not related to the common chip electronics serial interface. But the security policy parameter indicator, yeah, it's also not the security policy identifier of IPsec. That's what I was trying to interpret it as. The ciphering key identifier, key identifier, and so on. So we'll look at some of those later. What I want to get to here right now is the TAR, which is not the archive format, but it's the toolkit application reference, which is an alias for an application ID on the card. So basically, this is sort of when you send such a secure command packet to a SIM card, the TAR is like a port number, you could say, that defines which application on the card is supposed to receive the packet that you're sending. So when you install a Java or an applet on a card, and you want to have it accessible over this secured remote command packet stuff, then you also need to configure the TAR for this, not just an AID, but also the TAR, and the TAR then, which I think is 3 octets long, it's a 24-bit address, that defines sort of which application you want to reach on the remote, on the remote and on the card when you send to it. There's a couple of counters that relate to replay protection. And then in the end, you have also either some kind of CRC or a cryptographic checksum or a digital signature. That depends on what kind of security mechanism you're using with this. Now, the SPI has 2 octets. This is just from the spec. So a couple of bits define sort of, again, what kind of security you are wanting to achieve. So CC is cryptographic checksum, DS is digital signature. Oh, it's actually explained here. Your redundancy check would just be a CRC. Then whether you want ciphering or not, whether you want counters to do replay protection. So all of this is encoded in there. And every application, again, on the card has something called an MSL, a minimum security level. So the application can define whether, let's say, a CRC is sufficient or whether it wants a cryptographic checksum as a minimum security layer, or whether it is sufficient to just have integrity protection or whether it needs encryption. So the MSL, the minimum security level, is something that the application on the card defines, and then it is checked whether the security, this SPI actually fulfills the minimum requirements of the MSL, the minimum security level on the application. And only if you are at that level or higher security, then that gets passed. So the second octet defines whether you want a proof of receipt. That's sort of a confirmation that, don't need to explain that. And then also whether the proof of receipt should again be ciphered or not, or cryptographically authenticated or digitally signed or whatnot. So that is what the second octet. So the first octet specifies basically the command, and the second octet specifies the security level of the response that you get back. And then we have the the KIC, which defines which cryptographic algorithm is supposed to be used. Well, single DES, triple DES, and single DES is deprecated, of course. Triple DES in 2 different modes, or AES. And then you can also have a couple of bits if you have multiple different keys to sort of identify which of the keys should be used here between the 2 cards. The KID, so KIC is for ciphering, and the KID is for the cryptographic checksum. Again, there you specify whether you want to use an AES CMAC, that would be the normal case today, or some legacy DES, triple DES stuff. The response packet does look rather similar. Well, we have again something like a message type, the RPA, we have the packet length, packet header, blah, 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 blah. The toolkit application reference, then basically in this case for the response, it tells you which application on the card originates this response packet. And then again, you have counter, also actually, so it's the padding counter here, that's really just how many padding octets are involved in their status code, and then the actual data that can be signed and or encrypted. So that's the generic format, and then we have the specs. So by the way, this is those couple of slides, this is TS102225 ETSI, and then we have the specific encodings for specific transport layers. And this group of transports, SMS point-to-point, SMS cell broadcast, and USSD, that's what we call SCP-80 in the global platform sphere. It would be called TS0348 or 23048 in the 3GPP or GSM specs. Basically 2 different terms meaning the same thing. Also took me quite some time to realize that. Originally when getting into this. Now in SMS-PP, it uses binary SMS, so we use 8-bit binary SMS, and which for funny reasons some operators don't support. It uses this user data header mechanism. For those of you who've worked with SMS, I see some smile back there in Vadim's face. You know user data headers. It is this contrived, I'll leave it at that slide. I'm not going to explain details of user data header encoding, but sort of it's the SMS user data part, which normally is supposed to contain user data information. Basically, there's a way how you can remove some initial part of it and put additional header information in there. So you have additional headers in the supposedly user data field. The funny thing, and I don't have a slide about this, but I find this so hilarious in this context, is that sort of like as a recipient of an SMS, how do you know whether there's a user data header in front or not? There's a bit that out of band signals you, the UDHI, the user data header indicator, that tells you if such a header is present or not, but it only exists in the direction mobile terminated. So the mobile originated direction does not have a user data header indicator. I'm not sure if they forgot the bit or they didn't have the space somewhere. So it's impossible for a, let's say in this card, SIM card originated SMS to say whether or not it has a user data header. So basically it's implied that if a SIM card originates it, there must be a user data header, because it's not possible to signal it over the SMS protocol. But it's only in the downlink to the SIM card that this can be signaled. So yeah, really weird stuff. Now, why is this relevant in the SMS case? The normal space where people encounter, if at all, ever in their lives, user data headers in SMS is concatenated SMS. That's basically how the fragmentation and reassembly over longer messages through SMS works. And that, of course, is something that you very likely also will see if you install a Java applet on a card, because it's a couple of kilobytes. How are you going to send that to a card? Well, you need, of course, to fragment that over multiple messages, so you have the user data header. But in addition, you have an additional user data header that relates to the fact that this is such a secure message to the card. So you basically have 2 different fields within the user data header. One of them is mandatory. So in a single SMS for the secure command packet structure, your user data header will look like this. You will basically have the information element identifier 70, which tells you that this is a secure command for the SIM card. And if you have multiple concatenated messages, then it's a longer user data header, because now you have 2 different information elements, one for the concatenated SMSs and the second one for that this is a secure packet structure. But actually, only the first SMS in the sequence, you have the user data header information type telling you this is a secure command packet and the header for concatenated SMS. And in all the subsequent ones, you only have the header for concatenated SMS, but not the other one. So it's a bit interesting, let's say, to fragment and reassemble this stuff. So for SMS cell broadcast, it looks slightly different. And here actually, what used to be the CPI, the command packet identifier, basically the message type, let's go back to the generic structure. So we see there is the CPI, where is it? There. The CPI is a 1-octet field that identifies that this is a secure command packet. And if you go to the SMSCB implementation of it, the SCI becomes the MID, which suddenly is 2 octets long. This is the second line here. So basically it says, well, the command packet identifier range, blah, 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 and so on, that is coded on 2 octets because in cell broadcast all the identifiers are 2 octets long. And basically those are message identifiers that specifically reserved. So if a phone receives a cell broadcast message to this with this identifier range from 1080 to 1009F in hex, then it gets dispatched to the SIM card and not is supposed to be dispatched to the SIM card and doesn't go on. Anyway, so I'll spare you the details. Again, of course, in SMS cell broadcast, there is another way of fragmenting those messages because cell broadcast has its own built-in mechanism for paging, not paging in a sense of paging a mobile, but the cell broadcast pages which consist of several segments and all of that. So, of course, they use the native mechanism to SMS the cell broadcast for doing this kind of stuff. So what of this SCP-80, and I'm skipping the USSD here for shortness of time. In PySim master for quite some time, we have the pysim.ota library, which contains a couple of different classes. First one is the OTA key set, which represents a set of keys. Normally, you always have multiple keys. In such a key set, it's the KIC, the KIK, and the KEK. Now, the KIC is the one used for ciphering, the KID is the one for message authentication, and the third one is used for key encryption, if I remember correctly. So if you upload additional keys, so the first 2 keys is easy, right? So you want to do integrity protection and ciphering, and you have 2 different keys for that. That makes sense. And then you have a secure channel, and then you can send secured commands over it. But if you happen to install a new key on the card, for additional security, you pre-encrypt that key with a key encryption key and then send it through the enciphered command and so on. So you have this additional layer, and that's why you have that third key in this OTA security. So we have another layer in there. So the key set represents those keys, and then we have OTA dialect, how I called it, and only SMS is implemented, so only the SMS point-to-point with all the fragmentation and that stuff. I didn't implement cell broadcast or USSD. And then we have the algorithms and DES, triple DES, and AES, so all the 3 that are specified there for both authentication and for encryption. And so that's the library code is in master, and there's a branch that is sort of stalled, where I have some initial application code that uses it. Well, there is some test code with test vectors in OTA test that needs to be converted to proper PyTest stuff, so we have automatic test coverage. Not sure whether I did that already or not, I don't remember. And then there's 2 programs. The one is called SMPP to SIM, which is sort of the idea that if I want to just play with OTA stuff, I don't want to start setting up my SMSC, MSC, BSC, BTS, and so on, and all of that stuff, just so I can test SMS to the card. But rather, I want my card in a smart card reader that I attach to my laptop or whatever device it is. And then I want some program that offers an SMPP interface that I can send SMSs to. So I can short circuit all of the mobile network, and that's what this program is doing. So you can just send SMSs to an SMPP port, which is then picked up by this Python program, which does all this conversion stuff, because of course SMPP has again different encoding than the normal SMS, as we all know. So it does all the transcoding, and then also the delivery to the card, which is, I don't think I have the time. Is really almost a talk in itself, how the SMS that gets received by the mobile phone, how that ends up on the SIM card. Because it's not like you could think, okay, maybe they do it the way how traditionally, you know, when SMSs were still stored on the card, it just writes it to a file somewhere. No. You need the entire proactive SIM infrastructure and so on, where then an envelope command and additional encoding and so on, how sort of the phone is able to communicate to the SIM card that such an SMS has been received. So all of that is also implemented in there. The second tool is the VPCD to SMPP PI, which is sort of a work in progress tool where so VPCD is a virtual proximity coupling device. That is something that another project from Frank Morgner originally came up with. It's a very simple protocol how you can implement, let's say, a virtual smart card and make that appear as a PCSC reader in your operating system. And so this Python program uses this protocol, and on the other end it talks SMPP. So basically you can have a program that talks to a virtual PCSC reader, which then converts the APDU into this remote command packet structure that gets encoded into concatenated SMSs, which are sent over SMPP. And if you attach that to a mobile network or to the SMPP to SIM, that APDU actually goes all the way to the SIM card, and you can get the response back. So this is the complete onion in itself. So, okay, very quickly, I'll try to make it fast. The second, and today also more and more, and I guess the only, relevant mechanism is SCP-81. That's HTTP over TLS PSK. So it's like, okay, HTTP and so on. Yes, it really means the smart card itself speaks HTTP. It's an HTTP client. So there's HTTP client code in the smart card. Keep in mind, it's the client code. It's not the server code, right? So you have some external application somewhere in the network that wants to talk to a smart card, but it's not the server that can, so that is the backend that can connect to the card. No, it's only the card that can connect to the server. So you need some kind of triggering mechanism. And guess what? The only standardized version for triggering this is, remotely, is SMS. So you use the SCP-80 to send like an encrypted command packet over SMS, over this contrived mechanism, to the card to trigger the HTTP client in the card to make an outbound connection to the HTTP server. And this is the stupid, I'm not going to use the F word, reason why you need SMS in 5G networks, in IoT deployments, because there's no way how you can you can talk to the card using HTTP over an IP network without sending an SMS to the card first. So it's like, I don't know what they're doing. So anyway, so we have an HTTP post method that's used to fetch a remote APDU format string. So it's APDU gets formatted into a string that gets communicated over HTTP. And you have some special headers like the xadmin targeted application that sort of represents the tar. But then you don't use the tar like in the other transport method, but use the actual AID, because on HTTP you're not limited to 24 bits, so you can have a longer string, so you can use the full AID to actually do this. And some additional headers. Now, this is an example of the HTTP request, like from the spec. Of course, this has some variables that are not expanded in here and some optional parts. So this is the request that the card makes. And since, as I said, the card is the client, a request from the card has an optional section which contains the body of the previous response string. Because if you think of it, like initially somehow you trigger the card to make a first HTTP request. But then the card doesn't have anything to say to you other than, well, I'm requesting whatever command you have waiting for me. And then in the HTTP response, you actually send the command string to the card. And then when the card again sends the response back, it makes a request that contains the response of the previous HTTP thing, that exchange that has happened. So that's sort of the contrived mechanism. Now, and in addition, it's not, of course, plain HTTP, but it is HTTP in TLS. So the card, actually inside the smart card, there is a TLS implementation. Of course, it's not TLS 1.3, which everybody would want today, but it's TLS 1.0, 1.1, or 1.2, and it only uses pre-shared keys. So we're talking about, again, like shared AES keys in a normal situation. You see the methods that are also very limited support, only 128-bit and SHA-256. So that is what is implemented by the card. Now, I wanted to play with this, like I wanted to play with the SMS part. The problem is, well, there is no implementation out there, free software of this anywhere, and it's actually worse that TLS PSK is so exotic that I couldn't find any HTTP server, not Nginx, not Apache, not Light HTTP. None of the HTTP proxies that you can find out there can do TLS PSK to plain HTTP conversion. And then I said, okay, let's write some Python code, but no released Python version supports TLS PSK. There's a patch now in master, but they haven't tagged the release last time I checked yet. So it will be available in the future in Python. And many other projects actually refuse to integrate TLS PSK today because they say, well, in TLS 1.3, TLS PSK has been deprecated with a new mechanism, but then in reality, you know, there's billions of smart cards out there which use TLS 1.2 PSK, and projects refuse to implement it because, well, it's not relevant because it's not specified. It's not in TLS 1.3 anymore. Yeah. So that's sort of the situation with that. So somebody needs to find time and or money to get that implemented, and then we can finally speak HTTP with our smart cards. Yeah, this is the relevant specs, and with that, yeah, maybe a very quick question. I said we're already behind schedule. Thanks.
How does the SIM card request the remote server? So does the SIM card pass to the phone, please open a connection to this domain, or how does it work?
Yeah, that's correct. There is the open channel, or there's some proactive command that the SIM card will send to the phone, which the phone needs then to open the IP and port, right? The HTTP is inside the card, but the TCP, of course, connection needs to be created by the phone itself. And I think you can store some parameters on the card, some default parameters that will be used. Or you can also, in this triggering command, which I forgot right now the name, but basically the SMS that you can send to trigger the connection establishment, you can also include a port and IP address in this, so that the card then, when requesting, I mean, of course it checks the authenticity of the packet, but if it's correctly authenticated, then it will use this IP address and port in there. Yeah.
Thank you. One small note, TLS PSK is also used by dishwashers and other IoT things.
Yeah.
In your example with rooming, how does the authentication works for the network I'm rooming to when they update the IMSIs? But they shouldn't have the keys to my card, to the card, right?
No, this is all an application that runs completely on top. I mean, you have all your MNOs visited, home network, and so on. That is much lower. But then you have some MVNO on top that has IMSI ranges in multiple different countries with all roaming agreements to multiple other operators and so on. And they then remotely do all of that because they issued your SIM card, right? So they have the keys on your SIM card, and they, from some HTTP or SMS or whatever server, they can talk to code on your SIM card to do whatever and then change your SIM card remotely. So it's irrespective of the transport layer encryption of the mobile network. Okay, any other questions? Okay, good, then thanks.